Okay, we are live on YouTube. Your voice is breaking. Cannot hear. We'll quickly go through a recap. Yeah, okay. Yes.
Sir, am I audible properly now?
Yes, yes, yes.
Okay, sir. In the assignment in number 8, there is an parameter given, an excess noise factor Fm is equal to m to the power 0.28. This is the Fa or Fn?
This is the FN.
Fn.
Yes.
Okay. Okay, sir.
Otherwise, like, even though this week was a little heavy on theory, and like these are probably the most important parts for like link design. But like the assignment itself is not that difficult. All of the questions are based on receiver sensitivity and like one section on ETFA. So I hope as far as the assignment goes, there is not much trouble, but we will quickly go through the concepts that were covered in the week's content, and you have to be careful that all of the parameters defined in the assignment, or a lot of the parameters are defined in dB terms, but all of the equations that were discussed during the lectures are all in linear scale, almost all of them, unless specified that it is in dB scale. Almost everything is in linear scale, so be careful while applying formulas and all. So welcome everyone. This is live discussion on week 8. I see that a lot of people are not joining the Zoom meeting, but watching the YouTube video later on. If you want more interactivity, like, you can consider joining. Also helps me with motivation, and like if you have any doubts, like, it's highly likely that others will also have those doubts. So the first section of this week is focused on performance metrics for an optical communication system. We are discussing entirely based on on-off keying based system. We will discuss a little bit more about coherent communication and for example, QPSK signals. Those will be discussed briefly later on. But to get all of the concepts, we are starting with on-off keying signal, and we're doing a direct detection. And in that context, we define the performance metrics. The most important of them is bit error rate. Then we define a receiver sensitivity, which is the minimum amount of power required to achieve that bit error rate. Then we also define this quality factor Q, which is also defined in terms of the power levels that are incident on the photodetector and noise from the photodetector. And a related concept from the equations, you will see that they are very closely related, are Q and signal to noise ratio. So all of these concepts were first discussed considering only thermal noise, and then we also showed one example where we said the thermal noise was 0 and only short noise was present, and the number of photons were also low, so we used Poisson statistics, and we showed an example. When can you make an error? So some basic probability concepts were used. I hope all of you are familiar from bachelor level courses. Then we went on to discuss about erbium doped fiber amplifier, which you can think of as just a laser without a cavity. And so we discussed about optical amplifiers, like the three kinds that are popular. ETFA is the most popular, and there are some specific use cases where silicon optical amplifiers and Raman amplifiers are used. Then we talked about what is the requirement for amplification, how we need amplification if you want to reach long distances. Then we talked about what kind of parameters are of interest if we are either buying or selecting one amplifier to be used in our system. Like what are the parameters that we have to be aware of. So we talked about gain. Initially, we just said like unsaturated gain. Then later on, much later, we discussed like how gain can be saturated. There's a limit of how much gain can be provided. So if signal power is too high, like maybe you won't get entire small signal gain that the datasheet has specified. Then we talked about bandwidth. For example, what kind of wavelength ranges can you use that optical amplifier? Then gain flatness, how gain is varying with frequency. And one very important concept is this noise figure, how using this amplifier will degrade your signal, you can say. It will add some noise. You can consider it as white noise. And then we also said that we want our amplifier to have no polarization dependence, low crosstalk. So if you are amplifying two channels, like there should not be the effect of one channel onto the other channel. And pumping efficiency is how efficiently it is converting pump electrons to excite the erbium ions to, in our example, like how efficiently is the pump achieving amplification. Like we mentioned in class that the first erbium doped amplifier used some 80 kilowatt or something as pump, and but nowadays you'll be spending like watts of power to achieve the same small signal gain. Then we just explained how this erbium doped fiber amplifier works, very similar to laser, but we are pumping optically. So we showed this band diagram for this the three-level system that the ETFA uses. Then absorption and emission spectra, which is from the equation, you will see that there is a term that is varying with wavelength, and it captures how much power is, how much gain you can expect to get from the ETFA. Then after introducing all of those equations and showing this gain spectrum, we also discussed how ETFA doesn't give a flat gain. So we do some additional filtering to achieve a flat gain. Then we discuss about this signal saturation. This will basically limit in what region of operation you can use your device. And then we discussed about the primary impairment. For example, this amplifies spontaneous emission and the noise degradation that happens at each ETFA is why we're limited to say like we cannot send an optical signal to like multiple thousands of kilometers. That becomes challenging simply because at each ETFA site you are restoring the signal, yes, but you're also adding noise. So at one point, like the signal will be buried in noise. So after some like large distance, you're not restoring the signal. You will have to convert it to electrical, like demodulate and again encode. So if you want to send some like 10,000 kilometers, like a you can consider that for some transoceanic links, for example, sending from US to maybe Europe. Like those distances are very large, so their sending their transmission can be challenging. So be aware of that. Then we discussed about the primary noise source for EDFA, which is a signal ASC bit noise, and we ignore the ASC bit noise. And we talk about this noise figure and SNR degradation. So these are all of the formulae. So a common criterion is when you design a system, you need bit error rate lower than 10 to the power minus 9 or 10 to the power minus 12. Those are the commonly seen figures. Then this is the definition of receiver sensitivity. And then probability of error while sending a bit. Here we are talking bit and symbol are the same here. In case of like QPSK, bits and symbols can be different. You will be talking primarily in terms of symbols for QPSK. Here we talk about OK signal, like sending bits. So probability of error will be probability of like you can think in terms of set theory, like probability of error, and we're sending a 0 or some with probability of error and we're sending 1. So this expression, if you expand, you get this conditional probability. Each term will look like this. Probability of 0 we can assume to be half, because there is no reason why 0 or 1 should be like more probable. And okay, this I forgot to add it. Then probability of error given 0 will look something like this. Will look something like this actually. And probability of error while sending 1 will give this expression. And you can simplify if we say that ID is equal to halfway point of I1 and I0. Basically, ID equal to I0 plus I1 by 2, if you assume. It will simplify to this this expression. And for Q, large values of Q, you can also approximate using this expression. But you can find this complementary error function values for like these values are tabulated. You can find the values. Then how to find this decision threshold, this ID value? What is the optimum ID value? That for that you can use this expression and also a simplified expression. This sigma 1 I1 plus sigma 0 I0 by sigma 0 plus sigma 1. That expression also, I think one of the assignment questions uses that. Then for thermal noise limited systems, we discussed the case where sigma 0 and sigma 1 are same. In that context, what will be the quality factor? Quality factor definition is this. And when ID is I1 plus I0 by 2, then this quality factor Q expression also simplifies. Then some of the common figures you should remember is Q is equal to 6 for beta rate of 10 to the power minus 9. Q is equal to 7 for 10 to beta rate of 10 to the power minus 12. I think these expressions like you will be using for calculations this week and next week also. Or anytime you want to design an OK system, you will be using these values. Then receiver sensitivity you can achieve from Q values using this equation, which just comes from the definition of Q, where I0 we've assumed to be 0, and sigma 1 and sigma 0 both are this sigma thermal. And SNR in linear units is just Q squared. And the short noise limited operation, that example we discussed, there the bit error rate is related to the average number of photons with this expression. Average number of photons per bit is NP, and then bit error rate you can find using this expression. Then the ETFA equations, which are similar to lasers also, and this is the emission cross section. Then small signal gain will be defined something like this. But we try to simplify using this inversion D. So using this, the small signal gain simplifies to this expression. Maybe can turn out useful sometime later. Then E out, and this is the basic understanding of what is happening because of the optical amplification. Then this is the bread and butter, the amplified spontaneous emission noise you can quantify using this expression, and the noise power will be just this power spectral density multiplied by the bandwidth. Then we also define this NSP used here, and just for some simple calculations, you can also use this the AAC noise power. You can find out using this expression, which basically is just application of this where delta F we have defined to be 12.5 gigahertz, 0.1 nanometer. So this is for some quick calculations on the field. And then this optical noise we want to translate into what is detected at the photodetector, because that is the signal we are detecting and trying to demodulate. So the noise available at the noise impairments at that point is what is most important. So there we try to quantify what is the noise. So we will be receiving the signal and noise component, and photodetector will find the electric field intensity. So it will be the mod square will be used. So because of that, there will be mixing. So you will have this signal square terms, which is the desired term. Then one noise term will be signal times signal beaten with the AAC component. That is the signal AAC bit noise. And another component will be AAC bit noise that we ignore because we expect this AAC noise to be low. in the video lectures, I think we have used this rho AC times delta F we have used, same as this, but you have to be uh, careful about what is being discussed. Like my drawing tablet is not working. This figure was used. So what we said was this distance is delta F we defined, but the noise contribution for this small section, this was also written during the video lectures as delta F only. But to differentiate this from this, differentiate that to the detuning, we can use some other expression. That is what is being used here. Like understand where these contributions are coming from. So at delta F distance, a small delta F section will contribute this much to noise. And then what does the entire band contribute to noise? So you'll have to find the integrated noise that will give this expression finally. Power will be this PSD times delta F, you can. So be careful about these concepts. Then we calculated the noise figure using just this definition. These are again, all of these are in linear scale, so be careful. SNR we usually specify in dB scale. So this expression is valid for linear scale. In dB scale, you will have like SNR in minus SNR out. That kind of like division will become subtraction in log scale. Just that. So these are all in linear scale. SNR in will be this much, only using only short noise. Then SNR out will be this power output is getting changed. And signal AAC beat noise will also contribute to the noise. So the key takeaway is that this noise figure you can calculate using this expression, and we are fundamentally limited by this expression. So this F1 noise figure can never be below 2, or in dB scale, like F1 noise figure can never be below 3 dB. But when you add like multiple stages of gain, like this is Freeze equation, this is valid for electrical systems also. So you will see this in RF systems also. So when you first receive a signal, the first electrical block that you use is always a low noise amplifier. So that is because like the noise figure of the first RF component will contribute its noise figure, but if this first stage also has large gain, then subsequent blocks will contribute low noise figures. So in an RF chain, you will have the first stage will be a low noise amplifier. Second stage can be a mixer. Then there will be some other filters also. So even though the like later components are not so low noise, because we are using the first component as this low noise figure and high gain, the contribution from the other components can be like lowered. Uh, similar uh, similar concept is used here, but like here the other stages are also like identical. But we want alpha noise figure to be low, and then because of the high gain, like the contribution from the subsequent alphas will be lower. So alpha 1 will dominate like what is the final noise figure you're getting. These will also degrade, like it is not some constant noise, but the degradation is like not some linear expression, like it is getting scaled down by G1. So how you can think is in terms of like, this is the graph that was shown in class, that signal power is launched here. It goes down to this receiver sensitivity level, and we restore it to the maximum allowable power, like before going to nonlinear regime. Then again the signal degrades, again we restore, and we keep going that way. But at the same time, the noise, the optical noise will remain, like due to spontaneous emission from the source, you will have some noise level. Then because of this alpha, this noise level will go higher. Then again, using the second alpha, again this noise level will go somewhere higher. So after some point, like signal can get buried in noise. So after that, like you cannot, like you can only use amplification till you have your signal power more than noise power. So that is how we use the alpha. These are the equations. I think there were like 3.5 hours of content this week and a lot of equations. I hope you understand all of them. Make sure you understand. There were some uh, jumps taken during the lectures, I think. So make sure you can fill in the gaps and understand like, how we are arriving at this formula. That's pretty much it. If there are any questions from the YouTube side, you can ask in the chat. Or use the discussion forum also. Like, submission is tomorrow only, so we have time. Again, next week is finishing our discussion about link design. So if you're asked to design a system, like this week's content and the first half of next week's content, that is what will be most useful. So link design is like one of the key takeaways from this course. So make sure you understand this week's content and first half of next week. Then we go into nonlinear phenomena next week. That discussion is also important, which is like discussion on why we try not to go above this some limit set by the nonlinear phenomena. if there are no questions, we can just close, and you can use the discussion forum for questions. I use 1550 nanometer for this all of the calculations because we're talking about communication. That's a reasonable assumption, sir.
Thank you, sir.
Okay. Okay, then we'll close, and if you have any more doubts, you can ask in the discussion forum.